Flack math! Give me some math and I'll give you some flack. Flack math!
Okay, we are going to talk about counting principles. I know it sounds weird.
That's what now you get it.
Yeah.
Great.
Counting principles.
Just takes one.
Okay.
You could listen to that.
What just happened? I don't even know.
Okay, let me just read these definitions. You don't have to write these down. These are pretty self-explanatory. But in counting theory, an experiment, quote unquote, experiment, is any process that results in one or more outcomes, as in quote unquote outcomes. Okay? So you have a certain number of outcomes in an experience or experiment. If a process is repeated one or more times, each time is performed as something called a trial, and the experiment consists of all the trials. So, for example, you could see how many times you get a heads when you flip a coin 10 times. So you have 10 trials of flipping a coin. Let's put the food away. No eating in class.
What? Look, Mr. Flack.
But you know I don't survive.
Never been eating in class.
What
Take
about-
one last bite and then put it away.
Yeah, you're not allowed to eat popcorners in
I feel
your
like we've been
classroom.
eating in class like the whole semester
Yeah,
so
like
far.
I know, sorry.
I know I have.
A cafeteria offers turkey, ham, and chicken salad sandwiches. Okay? Here's the twist. The bread choices are rye and wheat. So how many different outcomes could you have if you did that? So what we're going to do is we're going to use a tree diagram. So you could have turkey on rye or wheat. So turkey, rye, wheat, turkey. What was the other one? Ham.
Six total.
So you go rye, ham, wheat, ham. So how many different outcomes are you going to have?
6.
Okay. Because
Or it could just be rye, or just wheat.
well, that's not an
That
option.
should be 8 though.
It has to be a sandwich.
Yeah, you got to order.
I mean, you can have a.
Can't you just have
nothing
bread and bread?
sandwich.
Bread.
I guess is it? Yeah, it's chicken salad, chicken rye chicken. Sounds like raw chicken. And wheat chicken. Okay, so you can use a tree diagram to do that. If you flipped a coin 2 times, if you flipped a coin 3 times, how many different outcomes could you have? If you flip a coin 3 times, what?
18?
Not 6,
18?
not 18.
Wait, oh.
So you could try you could just kind of do this combination.
7.
So you could go all heads, right?
Oh, yeah.
You could go heads, heads, tails. You could go heads, tails, heads. You could go tails, heads, heads.
Oh.
Okay? And then let's say we have 2 tails. So we go H, tails, 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 H, tails, 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 H. And then the last one, tails, tails, tails.
Mr. Flack,
How many is that? Yes?
the water fountain doesn't work.
Okay.
Well, like
8.
you know in the comics when you get the teacher to fix the water fountain.
What?
What? No.
What comics are those?
Maybe just like cook it again.
What comics are you reading?
Just like graphic novels. I don't know. But the water fountain doesn't work, and you're supposed to get your math teacher. That's what I read. It's American culture.
An American ghost ship.
To school.
Fix the water fountain.
Sorry.
No.
He's not an electrician.
Yeah.
Wow.
Do you want me to,
Why are you so thirsty? Oh, is it because you were eating in class?
No, it's because I forgot my water bottle.
Yeah.
Again.
Okay, so a sample space for an experiment is the set of all possible outcomes. So here's the sample space for ordering some kind of chicken salad at this cafe. Here's the sample space for flipping a coin 3 times. These are all the possible outcomes. There's nothing else that you could get that's not listed here? Yes.
Side.
You can't.
I've done
There's
it.
no hypotheticals in counting theory. There's no
Why
hypotheticals.
not?
Because then your if statement isn't, if you flip a coin 3 times, these are your possible outcomes. So that does not include, what if you flip the coin and it lands on its side and it doesn't go on one side? No, I said if you flip a coin 3 times, these are your possible outcomes. Okay? So an event is any subset of a sample space. Okay? So this could be an event. This could be an event. You could have like, what's the event of getting tails twice, and it doesn't matter what order. Well, there's one, there's one, there's one. So there's 3 different events, or there's one event of getting tails 2 times. Okay? All right, if you need only to count outcomes rather than actually show them, one method you can sometimes apply is the addition counting principle. Okay. Suppose a trial can result in n outcomes for one category. Okay? N outcomes for one category, n 2 outcomes for another category, and so on. If there are k different categories, then the total number of outcomes would be this: n1 plus n2 plus n3 plus ... plus nk. Okay? So that makes sense. So far, it's all making pretty logical sense. All right, we're going to draw an ace or a face card by drawing a card at random from a standard deck. Okay? So, the events draw an ace and draw a face card are mutually exclusive. There's no aces with faces on them. Okay? And there's no face cards that are aces. Okay? No, it's either
This
ace,
deck doesn't.
king, queen, jack. Okay? So those are,
What's face?
they're exclusive.
Oh, just like
A face
Like a young
king queen.
What's, and if you're talking about cards, you could say, you could draw a 7 or a heart. Are those mutually exclusive?
No.
No, because there is a 7 of hearts. They have something in common. Okay? All right, so here's the deal. How many outcomes for an ace? 4. How many outcomes for face cards?
16.
12.
12.
Oh.
Yes!
So total-
It's at least 12.
No, it's
Total of
16
16
because-
total.
No, because there's
Kings-
4 sets
kings,
of
queens,
4
and
face
jacks.
cards. There's
No, because
4 suits.
There's only 3 face cards.
Oh, right. I'm counting
Just the ace.
jacks. But...
Yeah. Well, you can count jacks. You just can't count aces. King, queen,
Oh,
jack.
I'm sorry, jokers. There's only
Oh,
3.
yeah.
Hoonigan.
Okay, so there's 16 outcomes in the event. Draw an ace or draw a face card. Okay, what about this? Draw a prime, or choose a prime number or a multiple of 6. Or, oh wait,
Those aren't mutually.
or a multiple of 10. Okay, so choose a prime number, a multiple of 6, or a multiple of 10. What's the problem?
They're not mutually exclusive.
Okay, but if I say between
Oh.
1 and 20, then you're safe, right?
Uh-huh.
But if you just say multiple of 6 or multiple of 10, well, you got 60, you got 120, you got all the multiples of 60. Okay, so a prime number, multiple of 6, multiple of 10. So all you have to do is count the prime numbers between 1 and 20. What is that?
2.
2, 3, 5, 7, 11, 13, 17, 19. What is that? 8? And then how many multiples of 6 are in between 1 and 20?
3.
6, 12, 18, 3. How many multiples of 10? Technically, it would just be 1 if you're talking about between.
But 20 is
But-
in between.
I wrote the problem down wrong. 20 is not in between 1 and 20.
You're right.
But 1 through 20, 1 through 20
There it would be.
would be 2. Okay, so what is that? 11 plus 2 is 13. So the answer would be 13 outcomes in an event choose a prime number or a multiple of 6 or multiple of 10.
THRU?
Okay,
That's not correct.
so the fundamental counting principle uses multiplication instead of addition. All right, this is good. Fundamental counting principle. Here's the deal. Suppose k items are to be chosen. If there are n1 ways to choose the first item, n2 ways to choose the second item, and so on, then there are n1 times n2 times n3. So k items chosen, n1 times n2 times n3 times ... n to the nk ways to choose all k items. So these principles are fine and dandy, but it's easier to just use some examples. So how many passwords are possible if letters may be repeated? Like if you had a 3-letter password. So let's do example 3A, 3-letter password.
Mrs. Kopp, attendance, please. Mrs. Kopp, attendance.
How many different possibilities are there? So here's what I like to do. I like to write blanks. Okay, so I'm writing the blanks. How many choices do you have for the first letter? 26. How many choices do you have for the second letter? 26. And how many choices do you have for the third?
26.
This means multiplication. So let's go back to the how many choices do you have when you flip a coin?
1 and 2.
You have 2 choices. So if you flip a coin 3 times, 2 times 2 times 2 equals 8. Okay? That's how many different possibilities there are of flipping a coin 3 times. How many possibilities are there flipping a coin 4 times?
16.
16. 2 times 2
At
times
least
2 times
12.
2. At least 12. Okay, this is a big number. Somebody want to do that?
Yeah, it's like 7.
What do you got?
17,576.
Whoa! You're going to be there a while if you forgot your password or you're trying to crack into somebody's thing. Yeah.
Which means I went and did the math. More than 208 billion possible combinations for a 8-letter passcode with a 4 numbers at the end and 1 special character.
Yeah, that's crazy. Okay, and at the end. And there's way more if those numbers can be anywhere in there. Okay?
Here's the. Can I ask something?
Yeah, ask something.
Naturally, that means like a 4-digit pin is way less secure, though, right?
No,
Well-
because there's infinite. No, wait.
It's just 9 to the power of 4. 9 or
Right.
0 to the because you can use 0, so you can use
So
10 to the power of
10.
4. So that's
10 to
just
the power of
10,000 possibilities.
Okay.
Yeah.
That seems a lot
Unless-
better than the number I got. I got 6,561, which, like, it should be at least 9,999.
Okay, how many would it be? Guys, let's look at this. How would you figure out the passcode if you cannot repeat a letter?
Well, it would be 26, 25, and 24.
Yeah, 26. Now you've already used one, so now you only have 25 choices for the next one. 24. I think this is the easiest way to do this, is to kind of put blanks and say, okay, how many choices do you have for the first one? How many choices do you have for the second one? This is a little bit less, but still a lot. 15,600 different possibilities. Okay?
Just getting
2 events are independent if the probability of one is not affected by the other. So independent events, and this is where the hypothetical situations don't count. Independent events are like flipping a coin. If you flip a heads 10 times in a row, what's the probability that you're going to flip a heads on a coin the next time?
1/2
Still just 1 out of 2. Okay? The coin doesn't say, I'm so tired of laying on my face. Please don't. I'm gonna try to move and land on my tail instead of my face. No, a coin does not have feelings or a soul. Okay? I'm sorry if you're attached to your coin will not be with you in heaven. All right? Independent events do not affect each other. Do not affect the outcome of each other. Do not affect outcome of each other. If it did, then that would be a different deal. Now, here's the deal. This second letter is not an independent. Is it an independent event? Because it's affected by this one. It's going to have less available options there. Okay?
What if you already know what the first one is? Then it would only be like 26 times 26.
Yeah, it'd be 25 times 24 if you can't repeat that first one. But yeah, that's significantly less.
Yeah, it's only like 600.
Okay? So dependent events do affect each other. Okay? All right, ready? Letters A through E. Letters A through E are written on 5 index cards. Okay? So you got like, here's A, here's B. If you ever get confused by this, just draw some pictures. D,
That's
E. Okay? Letters A through E are written on 5 index cards. A card is chosen at random, and then another card is chosen at random. Determine whether the events in each case are independent or dependent. Here's situation A. We choose A, then we choose B. If the first card is replaced before the second card is chosen.
it's independent.
Okay, so they're independent because the first choice didn't affect it. We put it back in, we shuffled it up. All right? So this is like independent events are like we call with replacement. That's an example. This is just an example of an independent event. When you pick a card and you put it back in the deck. Okay? Without replacement, those are dependent. So choose A, then choose B. The first card is not replaced before the second card is chosen. That's a dependent event. Okay? All right. This is what I always share whenever I talk about probability. And this usually keeps people from going up to Black Hawk or Central City.
Oh.
Okay? Because gambling doesn't ever pay.
Wait,
Okay.
it does, Mr. Flack.
Of
Because-
course it does.
Wait,
There's
wait.
there's a chance.
No,
It
I had
pays
something
an
else to say.
addiction.
If
You
you,
can cheat.
go, if you go to the casino, if you go there, you get like a free dinner if you play. So
Oh, nice.
Oh, so you can lose your money while you get a free dinner.
no, you just play
It's kind of
once
like
for like
the
$10 and
rewards
you get
points you get for using a credit card. Is it kind of like that?
you just like
Gas points for having
I don't
a
actually
superstar.
like.
Every $100
Okay,
you spend, you get 1
real
cent
quick.
off gas.
Let's do this real quick. What are the odds that you are sitting at a poker table and you're like, I think I just feel really good about this. I feel like I'm gonna get 4 aces in a row.
0%.
You're more.
You're really bad at
Okay, well, first of all, let's do that math. What is the probability of drawing 1 ace out of a deck?
1 over 52.
No.
Why not?
Or
4 out of 52. Okay, now you have that in your hand and you're going, oh my gosh, this is gonna happen. What's the probability of drawing another ace?
3 out of
51.
3 out of 51. What's the probability of drawing the next one?
2 out of 50.
2 out of 50, 1 out of 49. Let's do some cross reducing and vertical reducing. So this is 125. This is 1 and what is that? 17. Okay, and then 4 and 52 is like we can take a 4 out. Oh, we can take a 1 and 13, right? So then let's do that math. So that's 1 and 1 and 1 and 1. So 1 over, what is this number? Who's got it? is it?
Oh my
Sam?
gosh.
5,525.
I don't.
Not happening.
I don't think we did that right.
Wait, is that? I'm sorry, that's my bad. Give me a second. I forgot to do the 49.
270,725.
So, yeah, you could get 2 aces. There is a chance, 1 out of 250,000 chance that you could get 4 aces. So go.
But 2 aces.
Go all in. So I'm gonna get just when they, at the river or whatever the first one is in Texas Hold'em. Just go all in. You got a chance. Okay. Did anyone see Dumb and Dumber? It's like what are the chances of you and me getting together? Like 1 in 10. I would say more like 1 in a million. And so he's like, so you're telling me there's a chance? And he's like all excited because she told him he had a chance with her, a 1 in a million chance. Well, this isn't quite that bad, but it's pretty bad. 1 in 250,000
But
chance.
to
is
get
not
2, it's only 1 over 221.
good. Yes.
That's the highest I've ever gotten this thing.
Sarah, did you have a question?
I was just gonna say the highest playing poker I've ever got is
Whoa. You play poker?
I do.
Hasn't
But I
everybody?
don't play for stuff because
But like, you play for money
no.
in casinos?
Yeah.
Yeah.
I look
Okay.
18.
Mm-hmm.
No,
They're just like, oh, you look old enough. You can come in.
All right, let's do
Pretty
34.
sure you can do it with a parental figure with you.
Yeah.
you're allowed to play as soon as you.
We're gonna graph linear equations. This is part 2 of graphing linear equations. Graph linear EQs, part 2.
I hate linear equations.
How many parts are there?
At
2.
least
74.
At least
Okay.
12.
So we talked about linear equations. Why do they call them linear equations? Because
To break my back.
when you graph it, it's on a line, right? So this might be like,
Who knows?
can anyone guess what the graph of this equation would be?
Graph.
So y equals,
Y
or what the
equals-
equation is. You got one, Sam?
Something close to.
No, sorry. I can.
Y equals -3.
Well, wait. no.
-3/5.
Negative
We don't
1.
have any values, so there's.
Plus.
Yeah, we're just
Right
kind
now
of
there's
making
no way
some
to
good.
calculate.
We're making now there is.
Oh, -3 plus 4. Or -3/4.
Negative.
No,
1.
-2/4.
Negative
It's not calling.
2.
Yeah, Sarah, what do you got?
4?
4?
wrong?
Y equals
Just
4?
straight up.
No.
I got it.
No. never
Y
mind,
equals
you know.
-2/4 plus 2.
That's what I
X.
was gonna say.
Plus
2.
Okay, so remember, slope-intercept form. Calculate the slope. How do you calculate the slope? Go from one point to the other, but don't cut through the yards. You're going to go south 2, and then east 4. Down 2/4. Reduce 2/4.
1/2.
1/2. So you're going down 1/2, and then the y slope intercept. This is where it crosses not the x-axis, Sarah, but the y-axis. So that's going to be +2 is where it crosses.
I
Why
don't know.
is it
I
the
was just
x-axis
doing
is
it
the-
You
backwards.
just need those 2 things.
Because I
That's
just
okay.
always start with
4.
That's all you have to do. You just need 2 things. You need a starting point, and you need a direction. Okay, you need the slope, you need the intercept, and you need the slope. You need the slope, and you need the intercept. Yes.
I don't. See, the thing is, I don't have any besides 0, 0, the center point of the graph. There's no real value to this, so in a way, there's not any way to prove.
Yeah,
Whether
we're
it is
ishing
true or
we're
not.
ishing this, and we're going to. There's a whole unit on ishing a linear function. Okay, it's the unit called line of best fit, and basically we have to ish an equation. We have to come up with an equation that is an estimation of the line. Okay, And that's frustrating because it's not black and white like most math is. Like it's either right or wrong. It's an ish.
See,
And
we're
that-
just assuming that it's one.
Yeah. Okay, so a function with a constant rate of change is called a linear function, and its graph is a line. Every non-vertical line represents a linear function. Okay, so this is technically not a function. Why not?
Because there's nothing there.
Well, because it equals 0.
Because it is a vertical line,
Or
and it has infinite lines on the vertical.
yeah.
Yeah, the
if
vertical
you-
line test doesn't work because if you draw that vertical line, there's multiple y's for the same x. Okay, so this is an equation. It could be like this: x equals 3, but that is not a linear function. Okay, it is a linear equation, but it's not a linear function. All right, but the horizontal lines are great. So this one is y equals 2. And there is a slope there. It's called 0. You could put it in slope-intercept form, y equals 0x plus 2, which equals y equals 2, okay? So, you can determine whether each graph represents a linear function, first of all, by just looking at it. That is not a linear function, but you can determine the rate of change. If this goes to 1, 1, and then this goes to 2,
2.5.
2, 3, let's
Is it a
say.
function?
Then 1 goes to 1, 2 goes to 3. No, because look, you're multiplying by 1 here, but you're multiplying by 1.5 there, so it doesn't work. Okay? All right. So you can look at a graph and determine the function,
So
like
is
what
it-
we just did here.
It's still a function. It's just not a linear function.
This is still an equation, it's just not a function.
Yeah, but like the
It's a
curved
relation.
one, the curved one that you did.
Yeah, that's a
That was
function.
still a function.
Yeah,
It's
it's.
not-
I think it's a square root function. But so here's what you would see on your homework. Again, we've already been doing this. So you're just gonna graph.
You don't really care about each one.
3x plus 2y equals 12. How do you graph this?
I have literally.
Yeah.
Well,
You get
What's
the
the
X
easy-
on.
get the y
Yeah,
on
get
one
the
side.
Y on
You
one
could, yeah, you could
Or you
get
just move the x over.
2y equals negative 3x plus 12, and then divide by 2, y equals negative 3 halves x plus 6. And then you have it in slope-intercept form, right? So go up 6, 1, 2, 3, 4, 5, 6. Go down 3 over 2.
Mr. Black.
Down 3 over 2. Down 3 over 2. Or
That was only down one.
down
That's a
3
math
over
mistake.
2. Oh,
You
I
know, we
corrected it.
caught it for you.
Down 3 over 2. Okay, see, it looks like this, right? At 6, you go down 3 over 2, down 3 over 2, down 3 over 2. What's an easier way to graph this besides the slope-intercept form? Do you guys remember this method? It's already in standard form. You can easily graph
Oh.
an equation in standard form by doing what?
You like cover the Y and you cover the.
Yep. You do that. If you set x to 0, what happens to this equation? What's 3 times 0?
Nothing.
So what's y?
That was mine.
6.
6. All right, let's set y to 0. What's x?
2, 6, wait, 3, 4.
4. Now look, graph these 2 points. 0, 6, 4, 0. Connect the dots, you're done. Okay? So if it's already in standard form, use this method. All right? Cover the x's, cover the y's.
Okay.
All right? This gives you your x-axis intercept. This gives you your y-axis intercept. Okay? All right.
What if it was 3x minus 2y? Then
3x minus 2y, then x would be still 4, but y would be negative 6.
So
right?
just go the other way.
Yeah.
He's gaslighting you.
Okay, we've done this so much already. We don't really need to do it anymore, but I mean, we can if you want to. So let's try it. Like, this is when it's in standard form. I would just do it this way, but you can convert it to slope-intercept form if you want. But what happens if it's in point-slope form? Do you guys remember what point-slope form is?
No. Yes.
Here's what point-slope form could look like. Y minus 3 equals 1/2 parenthesis, negative 1/2 parenthesis, x plus 2. If it's in point-slope form, here's the deal. It actually gives you 1 point already, and it gives you the slope. Okay? If it's in this form, here's a point that's on the graph. So here's point-slope
Did it
form.
wrong anyways.
Y minus y value equals slope times x minus x value. Okay? So this is not x minus anything. This is actually x minus negative 2. And then this is y minus y value, so the y value has to be 3. So the slope, or the point, that the initial point that we have to start with is basically right here. Okay? And then I follow the slope, down 1 over 2, down 1 over 2. So this is my equation. Okay? So it's kind of like that horizontal shift in the mother function. It's the opposite of this and the opposite of this. Negative 2 comma positive 3 is your point, and your slope is still negative 1/2. Okay, so here's the deal. These transformations of f of x equals x. So here's the mother function of a linear equation. In other words, y equals x. What does y equals x look like? If you graphed it, yep.
Goes straight through the center.
Yeah, a diagonal line. Here's y equals x, or f of x equals x. Y equals x, okay? Now what happens when you add something? So what does f of
It
x
goes up or down 1.
equals x plus 2? Well, it goes up 2, just like it was. This is a vertical shift, right? This is just like that parabola. We shifted that mother function. Vertical shift is exactly what it says. But remember what it was? Like if you do something to the x before, then that is a horizontal shift, right? So if you had like, but with a linear equation, that doesn't really work. So f of x equals x plus 2. What's another thing? What if we did this? What if we did f of x equals negative x? What happens when it's a negative sign in front of it?
It goes down 1.
No. What do?
It,
You flip that mother function, right? So if I flipped over y, this y equals x, it would look like this. So this is y equals negative x. You flip it. So this is a flipper. This is a vert shift.
So what is
Oh, but
y
if you
equals
did
negative
f of x equals x minus 2, it would be a downward vertical shift?
Yep. Just because remember that's the slope. This is that slope-intercept form.
Okay.
The slope is still 1, so up 1 over 1, up 1 over 1. But the slope, the intercept is 2.
Okay.
So that's a good way to remember that for parabolas. That constant that you add or subtract at the end is the y-intercept, or is how much you're shifting up or down. Okay?
So what is
Yeah,
negative
okay.
y plus or equals negative x?
We just
that a thing?
Then that's still just y equals x, because you simplify the equation as y equals x. Okay?
It's a huge.
All right, what about this? What if you put a fraction in front of it, or a whole number in front of it? What does f of x equals 2x? What does that look like?
It would be double x.
Yeah, so remember what it was when we did the parabola? It stretched it vertically, and that's what we're doing here. 2x looks like y equals 2x looks like this. See how we're stretching it vertically. And then if it's f of x equals a fraction, f of x equals 1/2 x, then that would look like this. Up 1 over 2, up 1 over 2, up 1 over 2. So this is a stretch vertically. And this is a stretch horizontally. Okay? So the same kind of the same kind of transformations are happening that they were in with parabolas. Remember that? Okay. And then what you don't have here is you have like when this a or this coefficient equals 0. So y equals something like a constant. So y equals -2 looks like this, right? That's a vertical, nope, sorry.
Nuh-uh.
It is a horizontal line. I just ruined my nice diagram there.
No. Mr.
Y equals
Flack.
-2, looks like that. That's a horizontal line. These are horizontal lines.
Y equals something.
And it's kind of opposite of what you think, because when you think of y, what do you think of? You think vertical. The y-axis is vertical, but it's the y-axis because it measures how high something is. So and that's why I always mess up longitude and latitude. I can't ever remember which is which. I think longitude is the vertical lines, but it measures up or down, like how high up you are. It's just weird. Okay, x equals something. Remember, it's not a function, but it's still an equation.
Did you bring me food?
Is vertical.
Mr. Flack.
Vertical lines.
Mr. Flack, they brought me something.
Oh, thank you.
Yeah, very nice.
Thank you. Thank you. Thank you.
It was
You
just
guys-
mercy. You guys didn't do anything.
Thank you. It looks great and delicious. I'm going to eat it. Not right now,
should.
though.
Yeah, you should start eating it right now, Mr.
pieces.
Flack.
Okay, so
Black, there's too many shifts.
there's too many shifts.
And flips.
Too many, shifts and
Too
flips.
much that you can do with the mother function.
Yep. Okay,
I mean, when did you read this? Like,
So true.
so this is
What?
how is it I'm going to use this in life?
You won't. Just take a picture.
you actually. I'm glad you asked. You can when you design things, when you code things. There's a lot of this using
yeah.
coding, but I know you won't.
Math is very important
But-
for coding.
When you are trying to figure out like how to build a handicapped accessible ramp.
It
So
has
you
to
have
be
to,
15 degrees
and
or
what
lower.
it's gonna say it needs to have a 1/12, and no steeper than a 1/12 slope. What does that mean?
Stuff like,
I think they're building a
No, there's
handicap
people
accessible
rebuilding
ramp.
things downstairs. I saw them doing it.
up 1 over 12, right? It can only go up 1 and over 12. If it's any steeper, if it goes up 1.1 and over 12, then that is too steep. Okay? Yep. That's what it, or it can be a longer length, but it has to be at most 1/12, because 1/13 would be a smaller number, so it can't be any greater than 1/12 slope. Okay, that's pretty much all I got. The hardest thing to remember with graphing linear equations and reading linear graphs are the horizontal and vertical lines. Just remember that if y equals a constant, it's a horizontal line. If x equals a constant, like 3, then it's a vertical line crossing at 3 on the x-axis, okay? That's it.
Black man, give me some math and I'll give you some flack. Black man.